So, today the paper I'm going to be reading is Attention is All You Need, the incredibly famous paper introducing the Transformers architecture, right? And so this paper doesn't need that much introduction, so let's just jump right into it. We're obviously going to start by reading the abstract. So, the abstract. The dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. The best performing models also connect the encoder and decoder through an attention mechanism. We propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. And so, I should explain what recurrent neural networks are, because we know what convolutional neural networks are, right? They work really good on images. I want to explain what recurrent neural networks are. So, that's for other thing. So, a recurrent neural network operates on the idea similar to a convolutional neural network, where you have your input tokens, right? So you're obviously going to need a tokenizer or whatnot, right? And so what the recurrent neural network does is it effectively just operates on the nearby tokens, right? So you have, right? So these tokens in the next layer, I'm going to draw some arrows. This token is effectively, it gets information from only these two tokens. Then this token only gets information from, let's say, these two tokens, and so on and so forth, right? Kind of similar to how a convolutional neural network works, but, in a recurrent neural network fashion. Or, what other things have also been done previously in space, so I don't believe these are recurrent neural networks per se, is that, sorry, I should probably, that was a convolutional neural network, right? So I was explaining how that would work here. Okay, I'm just going to draw both of the things so it's less confusing. So, how does a convolutional neural network work for this, right? In essence, you have each token, and then it's similar to how an image works. Like, let's say you have these tokens as well, right? In essence, what you do is you just have a token operating on a small, I'm going to change the style of this to just be a line. Right, and so each token only operates on, okay, please just be a straight line. Right, and so each individual token will just operate on just the small area around it, right? So it's not actually going to operate across the entire space. It's not. Cool. Right, it only operates on the small area around it. It doesn't actually operate across the entire space, right? And then with recurrent neural networks, or RNNs, and then eventually this will just go into multiple layers until you eventually get an ending, right? Yeah. Whereas with an RNN, how it operates is that each individual token is affected by the tokens before it as well. So it's affected by the token from the previous layer, right? As well as the token that occurs before it in the sequence, right? And so now, in essence, what you have is the information of the text actually flows upwards through the RNN. Now, this leads to some issues, right? Like obviously, this leads to some issues because this is just a performance limitation, right? Because now, in order to actually find the token for this, like the value for, say, this token, not only do you have to calculate the token all the way back here, you also have to calculate the one next. So now, effectively, you're taking 3 token calculation cycles to calculate this token. It's very bad for performance, right? And because it's bad for performance, it's very difficult to train these models, right? Whereas with convolutional neural networks, now you don't have crazy dependency chains, but your tokens can't actually access the entire information space, right? So now they're just local tokens effectively. And so while that might have worked really well for images, the people were having issues converting that to text. And so with this paper, Hello? No? Oh, I clicked on an email by accident. Unfortunate. Basically, what this paper is proposing is effectively just using a transformers architecture. And we'll get to how that works a little bit later when they explain it, right? But they basically show that this is much better for English constituency processing and whatnot. So, introductions. Recurrent neural networks, long short-term memory, and gated recurrent neural networks have been state-of-the-art, right? Because CNNs, they don't really work for this 1D type stuff because you're not working with patches. You're working with the entire thing, right? And so they've been used sequence modeling and transduction problems. So basically CNNs, they work for images, they don't, and 2D stuff, they don't really work for text. For text, they use like recurrent neural networks and LSTMs. The issue is that recurrent models factor computation along symbol positions, and so in essence, to calculate the amount of computation for the hidden layer, you have to deal with the other layers there in there as well, right? And so attention is effectively a very useful case. But so what they're saying is previously people have done attention. It's just they're usually in conjunction with a recurrent network, so you don't really get the performance benefits of a transformer, right? Like the attention, it's there, but you don't get the performance benefits. In this work, they propose a transformer, which is a model architecture that just doesn't use recurrence, and instead just does entirely on attention, right? So you operate entirely on the attention mechanism, and you don't do any recurrent neural networks, so you get so much more performance, right? And they can reach the state of the art in translation. So this was originally a machine translation paper, and this later went into Google Translate, right? Paper run by Google, and it's being trained for as little as 12 hours on 8 P100 GPUs. So training these models, they are just like, hey, 8 P100, which are like pretty old GPUs. They're just like, hey, let's just like train it overnight and let's see how it goes. And it's like state of the art, right? Like imagine that nowadays, right? Like you like match GPT-4, you come up with a new architecture, you train it overnight, and then you just match like GPT-4, right? Or like Claude 3.5 Sonnet or whatever, right? And this is what the transformer architecture was able to do. You were able to scale very good. So the background, the goal of reducing sequential computation also forms the foundation of extended neural GPU, ByteNet, conv, right? So other people have tried, what they're saying here, is other people have tried to use convolutional neural networks as the basic building block, right? So they didn't use a different method, they were using convolutional networks. But that gets rid of global knowledge, right? So now it's only local. But also, in these other models, the number of operations required to relate signals from two arbitrary, right? They're basically saying the thing again, right? Like in order to scale up the context size, it goes up with a square. It's not super good, right? You have to increase the length of the model. In transformers, this is reduced to a constant number of operations, and so the cost of the reduced resolution due to the averaging is they use multi-head attention, right? They use multi-head attention to just solve the issue, and so they'll explain multi-head attention in a bit. So they're saying self-attention is really good, and right? Oh boy. And so to the best of their knowledge, the transformer is the first model relying entirely on self-attention, right? Everybody else, they involve these other things. Transformers, they entirely self-attention. They use it entirely. And so now I talk about the actual model architecture. Now, I'm just going to layer this as well, right? Embeddings you kind of have to have regardless, right? But there's some special stuff going on with the embeddings here that I'm going to label, right? So, the entire transformers architecture, right? Right, the entire transformers architecture, right? So you have your token going in, right? First, you go through. So now you have effectively two embedding steps, right? So because you're exclusively using attention and you have no natural view of direction in these models, what you kind of have to do is you have to embed information on both position and the actual text itself. So previously, the other models, they just had text embeddings. But the transform models, they also need position embeddings, right? Position embeddings, right? And so if we go back to the vision transformer, as we see here, the convolutional neural network doesn't actually need position embeddings, right? Because position embeddings are just kind of calculated automatically. Whereas vision transformers need position embeddings, right? They're kind of necessary to how they work. Same thing here. You need position embeddings to let the model know where is this actual token in the text, right? And so all of these, they enter this, both the text model, the text embeddings, as well as the position embeddings. Right, so they're in both of the embeddings. I am going to make those straight lines because this is kind of ugly. Right, and then those get brought back into, you effectively sum both of those up, right? So you take the text embedding and the position embedding and you just sum them up. Right, and so, again, this applies to all of these. Right. Again, make these straight lines. Right, and so you effectively bring both of these back together. So now you've basically taken the input tokens and then you put them into a latent space where that contains both the position of any given piece of text as well as the actual content of the text itself. Right? Then what the model does is it goes through attention layers, right? So you go through an attention layer, and then you go through a feed-forward layer, or I'm just going to call it a linear layer or an MLP layer or whatnot. So feed-forward slash MLP slash linear. It's not really a linear layer. It's feed-forward or like MLP, right? It's normally multi-layer perceptrons, right? And so, in essence, you now, like all of these, they go through, like, I'll just set the straight lines, whatever. Right, so first you go through attention. Then this just goes into the feed forward. And in essence, as the paper says, this just occurs n times, right? So same with RNNs, that just occurs n times. This, you just, in essence, you just repeat it, and then you can just like repeat it whatever many times. And then you have like an output like unembedding, right? Like, yeah, it's a linear layer. It's just a linear layer. This is just to do some like final calculations or whatnot on individual stuff, and then you have your output, right? So with RNNs, yeah. Again, I see Trojan Mango in chat. Hello. Yeah. So in essence, you have the RNNs and which are very computationally expensive. Then you have CNN-based architectures, which are not as computationally expensive. They're just not as good because you don't have like global knowledge. Like each token doesn't have global knowledge. And an attention is where the stuff has global knowledge. But what is an attention block? We didn't actually get to that yet, and we'll get to that later in the paper, right? So now you have encoder and decoder stacks, right? These are just like specifically how can you get stuff into the model, how can you get stuff out. Doesn't particularly matter. Next, attention, right? So previously you had scale dot product attention, but now they've brought in multi-head attention, right? So let's go in deeper on the attention block, right? And I'm gonna call this multi-head attention. Right? And so in essence here, how does the attention actually work? So if we go to the paper, we see that you have a V, K, and Q, and those go into H scale dot product attentions, and they get concatenated and just put back into a linear. Right? And so they have some fancy math here, but the easiest way to explain it is, so you have a certain number of, say, inputs, right? Inputs to the attention block. I'm going to make this smaller, so easier. Then you effectively convert it via just like linear layers, right? So you're just doing linear operations here, to a key, a query, and a value. I should probably just say input, right? This occurs on each input individually, right? You have the key, you have the query, and you have the value, right? Then what you do is, I'm gonna copy this. Let's say there's like 3 tokens, right? Is what you, okay, let's go down here. Where, okay, did they actually explain it well? No, they don't. Okay, so what you in essence do is you just multiply the key and query for any given thing, and you add it to the value, right? So what the thing here is this gets converted into the query multiplied by basically all the keys, and it gets brought back in, right? So the query. So here you have the query. You bring the query in, and then you bring in the keys of the other stuff. Right, and so then effectively, I should probably do this on any one given token first. And then you bring in the value as well, and that is the effectively, that is the output of your like attention block, right? So now in essence, any given token will be operating on every single other token, right? And so this is an n squared like operation, right? So like let's just say, so this is what actually limits the context window in all the new modern like transformer architecture things, right? Basically you have the model, and then you effectively, in order to say double the context window, you have to do 4 times as many attention calculations, right? Like this is the bottleneck on performance for all of these, right? And so this also occurs lower down, right? And so this is just regular attention, right? So like there's nothing crazily fancy here. This is just regular attention. So now what is multi-headed attention, right? So I'm just going to connect this up here as well. Right, and so then there's your outputs, right? Now, what is multi-headed attention, right? Multi-headed attention is effectively just doing multiple attention steps, right? So this is, so I should just say this is like single-headed attention block. Then this over here, multi-headed attention, right? What it is it's just like you I'll copy this input over, right? So you have your inputs, right? I'll just have them as input instead of just sending them through say one attention block. You send it through like 4 or 5, each doing like different calculations, right? And then you just bring them all back together, right? So I'll just set it as 3 so the diagram is easy, right? So you send any one of these, the input, you send it to like 3 separate attentions all at once, and then you just like, and you just like effectively bring it back as the output, right? So now each attention block, of course, it's like separately trained and whatnot. Right, and then now you have multiple attention heads, each like looking at all the stuff and whatnot, right? And so, yeah, and so then multi-head attention, you just do attention on all of them, and you like bring it all together. And so what this allows you to do is effectively you're able to do more like calculations per step and optimize the stuff, right? And so they do multi-head attention in a bunch of different ways, and so each of the layers, they have an encoder contains a fully connected feed-forward network, right? So this is a linear network. They have ReLU. This is just activation function. It's effectively just like a standard dense layer, right? They have embeddings, they have softmax, and then they have the complexity per layer, right? So per layer, self-attention is n squared times d, and so d is right. So d is the representation dimension. That's the embedding dimension, effectively, right? And n is the sequence length. K is the kernel size of convolutions, and R is the neighborhood in restricted self-attention. Nobody really does restricted self-attention, so you can kind of ignore this. But in just regular self-attention, they effectively say they move the square on the exponent from the representation dimension to sequence length, right? And so normally representation dimension is in the ballpark of like 700 to like 1,000 in modern day models, right? And the context window was the big issue there, right? And so let's assume your context window is like 1,000 tokens, right? Now this one scales like roughly 1,000,000 times if you just had like one token, right? It's 1,000,000 times bigger. Whereas with the other models, it's not like that. But in other models, it scales with your your embedding dimension. And so this is the reason many of these state space models are coming back, right? And so because those allow you to scale context much easier. But transformers lets you scale embedding dimension much easier, which gives you more accurate results, right? And so it's this thing of what do you actually want to scale? Do you want to scale accuracy of your model more, or do you want to scale the context window of your model more? And so it's a balance of like what you actually want to scale. And so then if you have a combination architectures like Jamba, then some stuff happens there, right? So now let's specifically talk about positional encoding, right? So since the model has no recurrence, no convolution, in order for the model to make use of the order of the sequence, they need to add some information. So they just have position encodings. And so here they force it as like sine or cosine, but you can just train that, right? So GPT-2, GPT-3, they just trained it. Here they just use sine and cosine. And they also experimentally learned and found that the two versions produce nearly identical results, right? So they're saying it's nearly identical, but as the models get bigger, maybe there's some stuff in there that comes out, right? And so they say they use the sinusoidal version because, yeah. Now they're motivating self-attention, but the main thing here is that with the way things are here, you don't have to choose between either having a very slow process or being forced into not having global knowledge of the stuff, right? So let's assume you have some. Let's just go through like where this comes into benefit. Let's assume you have a very large piece of text, right? And so let's assume you have like a character. He's like going around doing stuff. The name of the character is at the top of the text, and he does stuff at the bottom of the text, right? And let's assume there's some user. They ask what was the name of the character, right? But the name of the character is all the way at the start of the text, right? And so with a convolutional neural network, the amount of layers in your model effectively scales with where the name is, right? So first it has to go down and down and down and down. So if you say go down by 10% of the model each time, for that name to reach the bottom, you need a minimum 10 layers. But you're probably going to need a lot more, right? You're layer limited. And you can't do that much calculation in relation with the question on the name of the character itself, right? So you're kind of limited there. Whereas with recurrent neural networks, after one layer, the name is already at the bottom of the text, right? The information is passed down. But because you have a very long piece of text, you have to do a lot of computation, right? You have to do a lot of computation to actually get from the top of the text to the bottom of the text. And so now you've lost computational efficiency. With transformers, you kind of get both, right? You get both computational efficiency and you get like layer efficiency. But the problem with transformers, right, is that you can't scale that length up infinitely. That requires just more compute power. And that's why the RNN-based stuff is coming back, like Mamba, right? But at the time, in like 2017, when this paper first came out, and even up until now, the transformers are the best architecture for this type of stuff, right? Because they scale a lot better when it comes to like embedding size, right? And that's where like quality is. And so self-attention, they say, could yield more interpretable models. And we see this with stuff like the mechanistic interpretability that like Anthropic is doing, right? Like you saw Golden Gate Claude. They basically took the model and it turned the like effectively the idea of the Golden Gate Bridge up to the maximum, and they were able to interpret like the model and like what the whole concepts, and they were able to like turn it up or down or whatnot. Then they talk about the training regime. Here they only train on like 4.5 million sentence pairs, right? And so the vocabulary was 37,000. This is like a pretty small model, right? And they were obviously training English-French translation, right? And so each training batch they train on 25,000 tokens, right? And so for hardware, they train on 8 NVIDIA GPUs for like 12 hours, right? Like it's a very small training run, right? Like you could do this now for like $20, right? Like it's a very small training run, right? So they have optimization stuff, they have 3 times regularization, but they're basically saying here they have like the big transformer, right? Is like state of the art, it's the best, right? And the training cost is 10 to the 19. Now people are talking about 10 to the 26, right? The modern models are 10 million times more expensive training wise, but this is a start, right? They're able to beat the rest of these models, they're like 10 to 20, right? So when it comes to like quality, they're able to do like 10 times less. I guess here it's like 5 times less training for this, almost like 50 times less training than Calm S2S, and they're able to just outperform it, right? They're able to perform like the best, right? And so they have the result, it's the best in the world, right? And so then the number of parameters, they're measuring parameters in millions of parameters here, right? So nowadays we're measuring models in billions of parameters, or GPT-4 in like 1.8 trillion parameters. Here they're measuring it in millions, right? So their big model was only like 213 million parameters, right? It's a very small model. But they were able to beat all of these other models that are like bigger, right? Because they were able to utilize this architecture more effectively, right? They're able to take this new architecture they came up with, right? Just having attention layers. And then they're able to say, hey, look, we're able to beat all of these other people, right? Because they have the best model. And then they have different scales, and they tried a bunch of different stuff. And so here's the quality of the model, right? And so their base model, 65 million parameters, that was like that was a little bit worse than the other models, but it took like almost 300 times less training effort, right? Like they spent 300x less effort, and it was like pretty close to on par. Whereas here they spent 50x less effort, and it was like better, right? Like it's very like efficient architectures when it comes to the embedding dimension, right? Like in the big model, the embedding dimension was 4096, right? It's a big embedding dimension, right? Like even GPT-2 and 3 were like much smaller embedding dimensions, right? They had 6 layers on both, and they trained this for like 300,000 steps, right? Like they would it's a very small training job, like if you look at it compared to now. But they were able to be better, right? Then they see if they can generalize other tasks. So they perform an English constituency processing, right? So the output is strong structural. And so then they're like, hey, let's see if this would work. And they say, hey, transform generalize to English constituency processing, right? So they basically just said, hey, do autocomplete, right? So what all the like text generation models you have now, they're basically saying, hey, we're just going to do autocomplete on them. And that's what they did. And they got best-in-class results, right? Like multitasking, like generative, right? This is all generative. And they train on Wall Street Journal, right? So they just train on all of that. And so what they have here is effectively one of the first, this is the first transformer model. And they have the best in class, and they've made here the first transformer generative model, seeing if they can predict Wall Street Journal. And they trained it on both English and German and English and French, and it was state of the art, and it was the best. And so the code they use is at this link, right? Tensor to tensor. And so, library, so somewhere in here they have the code they use to train and evaluate the models. So this is the actual original transformer model, originally in TensorFlow. And yeah, so in summary, the attention is all you need paper effectively brought in the first attention-only model. And then they use multi-headed attention, which is just one attention but done parallelly simultaneously, right? So now you're able to use the GPU way more effectively and whatnot. And so now and then there you go. You have multi-headed attention. And they use multi-headed attention, and then they and so that's kind of the attention is all you need paper. Very foundational to the stuff we do now, and there you go, right? You have the foundation you need to understand a bunch of the models that are coming out now. From here, you can look at the GPT-2 paper, GPT-3 paper, very similar concepts, different like depths and whatnot, and yeah, I think I'm gonna end this stream here. Next stream I'll probably show off like a vision transform model I trained, and yeah.